Hey, let's start class. So today we will start introduction to the statistical learning. So what is statistical learning? Statistical learning is the science of learning from the data using the statistical method. Okay? And similar to the machine learning using the algorithms to learn from the data. Okay? So you can see there are differences. They both targets to learn from the data, but using different approach. Okay? And common question is, what's the difference between statistical models, statistic methods, and algorithms? So there's a paper, very well-known paper called Two Cultures by Leo Bremen. And if you have time, I can post the paper link in the Moodle after class. And if you have time, you can read it. But just in very briefly, so statistical models. So let's say what we have is a black box, okay? And we have the input x. It could be one x variable, two multiple x variable, that's no problem. And we have output, that's the response y, target of interest. And the black box represents the underlying unknown mechanism that you give me the x and I output the y. Okay, so the goal is to open this black box, which may not be possible, right? So what we do is, for the statistical models, we usually enforce some parametric form that had for the relationship between the x and y's. The simplest form in statistical models is linear models, right? Like multiple linear regressions. We force the relationship between x and y to be linear and additive, but we can also include some interaction terms. That's fine, but that's statistical modeling approach. What is machine learning algorithm approach? Machine learning approach is, instead of enforcing some parametric form, we use very complicated methods, algorithms, to approximate the relationship between x and y, so that we can have a fitted model which which try to approximate the underlying unknown mechanism as much as it can, but without any parametric assumption, assuming x is linear with y and so forth. And so that's the biggest difference. Okay, and we will talk about this point later also. But that's the difference. But here in our course, we will talk about both the statistic approach as well as the machine learning approach. Okay. So here is some examples to predict the stock price, predict whether a patient hospitalized due to a heart attack will have a second attack or not, right? And identify some risk factors for the prostate cancer. And given a collection of text document, we want to organize them according to their content similarities. So you can see the first two are based on the predictions. So focus on the predictions, right? And the third one is trying to understand some features for the black box, like what are the most important influential risk factors for the prostate cancer. And the last one, which you will see later, is called unsupervised case. Okay, so statistical learning plays a key role in data mining, artificial intelligence, and machine learning. And we can divide the statistical learning into supervised and unsupervised case. So the last one is the unsupervised. Okay, so what's the difference? The difference is for the supervised situation, we do have a response variable. Okay, at least one response variable. Sometimes we may have more than one. So we do have some target of interest, variable of interest. Okay, so we want to predict these values or estimate these values through the predictors, through the explanatory variable. So that's the supervised case. Unsupervised case is we only have X. We only have those explanatory variable. We don't have a particular response variable. Okay, so that's the unsupervised. And we will talk about both. Okay? So here are some data sets. Some of them we will use that in this course. This is the email span. So the response variable is binary, either spam or normal email. The predictors are 57 most commonly occurring words and punctuation marks in the email. And these are some average percentage of words or characters appears in an email. And this is their percentage in the email, in normal email, and in the spams. So you can see we do have some difference. Some of these words do have some discriminating power to identify the email is spam or normal email because they have very different distributions for among some of them. So the purpose is to predict the email is spam or not. Okay, so that's one data set. And another is the digit recognition. So this is a famous data set from the USPS. And these are the handwritten zip codes. You can see this is the data we have. So these are the image data. These are scanned as a 16 by 16 pixel image, grayscale image. So we have how many variables do we have? We have 256 variables, right? We have 256 because 16 times 16, that's 256, okay? And we want to use these 256 variables to predict the image is 0, 1 through 9. So this is called classification problem. How many class do we have? We have 10 class from 0 to 9, right? And we have 256 predictors, X, right? And the Y is a categorical variable, which has 10 class. And this is another example. That's the early detection for the prostate cancer, which is the #1 cancer killer for males in the world. And the early detection of prostate cancer is extremely important. And the mass spectrometry is a very common analytic technique for determining the elemental composition of a sample. So these are the mass spectrum for 2 patients. The blue one are the normal patients, have no prostate cancer, but the red one is the mass spectrum for a patient that has the prostate cancer. Okay, and for each mass spectrum, how many variables do we have? How many channels do we have? We have over 15,000 channels. So that means we have over 15,000 X variables. Okay, and we want to use these spectrum to predict, to early detect the patient has the prostate cancer or not. Okay, so you can see what are the special things for these three examples compared to those examples that you see from the classic statistics textbook. If you take the 7,005, 15s, you will easily find that in the textbook, most of the examples that you see, they have only a few X variables, right? And have just a few hundred observations. And these are the typical size for a data set in the textbook. But what about these? Like this one has over 15,000 X variables. And the sample size only have a few hundred patients. Okay, for this one, we have 256 X variables. And the sample size is, oh, I didn't, is about 20,000 something. Okay, and this one has 57 and a few thousand. So you can see the dimension or the size for these examples are very different. We have much more X variables than those in the textbook. And also the sample size could be also very large sometimes. And also like in this example and in this example, you can see there is a high correlation among the variables, X variables. Why? Because this is image data. Image data is well known that they have autocorrelation. They call it spatial correlation, right? So the neighboring pixels are highly correlated. What does that mean? That means if a pixel is dark, then the neighboring pixel is most likely to also be dark, right? Same thing like that. Okay. And for this one, we still have very strong high correlations. So you can see also the variables, they have high correlations among each other. So you can see we have more structure in these data sets, and also the dimension is much larger. Okay, so these are the difference, and that's why we need to have those new tools in our toolbox to handle this data sets. Because if the data changes, that means maybe we should use different tools. Okay, and in the computer science, there is a very interesting but well-known theorem called the no free lunch theorem. Okay? If you don't know, you can search that. No free lunch theorem says what? Says that in terms of those algorithms, okay, if we consider all the possible situations, on the average, no algorithm is better than the other. No method is better than the other if we consider all the possible situations. Okay, so that means what? For some type of data, maybe this method works very well, but that also based on the no free lunch theorem, that implicitly says that means what? In some situation, this method will not work well. Because on the average, all the algorithms, all the methods are essentially the same. Is that clear? So that means if we have some change in our data structures, data size, and the data properties, so maybe we should use new methods. And that also agree with the no free lunch theorem. Okay, we cannot just use one method applies for all types of data. That won't work. Some of them will perform poorly. right? Okay, so estimating the unknown function f, that's one of the main topic in the statistical learning, okay? So suppose we have y and x, and we have a very general model assumptions, okay? Let's say y is a function of x plus some additive noise. And this noise has the expected value equals to 0. And this is a very general assumption model with very flexible assumptions because we have no constraint on the f. F is unknown. It can be smooth. It can be continuous. It can be linear, non-linear, whatever. We have no restriction on the f. And that's a very general model which applies to many places, right? Okay, so let's see an example. So here we have two variables, two x variables. One is the year of the educations, one is the seniorities, and the output, the response variable is the income. We want to fit a model to estimate the employee's income level based on their years of education and their seniority. Okay, and this is one of the models, and obviously this is a nonlinear model. And you can see there are some dots are above the surface, fitted surface, and some are below, right? So you can see like this dot is below, but these dots are above the surface, okay? So you can see here, this is an example that shows y equals to fx plus epsilon. So what is the f? F is that hyperplane, is that smooth surface. Okay, and what is the epsilon? Epsilon is the vertical distance between the uh, the red dots, which are the observed data point, to the fitted surface, fitted value, and that's the uh, epsilon. And obviously, the one that above the surface has the positive epsilon, and the one that below has the negative epsilon. Okay, so that's the example. And we will go back to this example in a minute. So estimating the unknown function f. So ideally we want our fitted f to be very accurate, right? However, the accuracy of estimating the f depends on lots of factors. So here are the tools that I showed. These are the, one is the size of the variation for the epsilon. One is the complexity of the fitted function f. Okay, so the size of variation for the epsilon. So epsilon is the additive noise, right? So here, a common assumption is besides the expected value for the epsilon is 0. What does this mean? What does this expected? So that means on the average, the epsilon is equals to 0. So that means some of the epsilon are positive, but some are negative. But if we add them together on the average, it will be around 0. Okay, so that's the. Beside this assumption, we also have some an assumption that a common assumption is the variance for the epsilon I is a constant. So so the variance of the epsilon is a constant, sigma square. Okay, so that's another common assumption we had. And that sigma square is called irreducible error. Okay, so this epsilon is the irreducible error because we cannot reduce that. That is building the data generation mechanism, right? That is embedded in the data that we observe. Okay, so that part cannot be reduced, cannot be removed. Okay, so the size of the variation for the epsilon, so that means the sigma square. So that's the size of the variation for the irreducible error can affect the accuracy for the estimated f. Okay, and that epsilon is, in practice we call it what? And that size of variation in practice we call it data quality. Okay, so if you have a data set, people say, oh, this data set have a bad quality. Usually that means the size of the variation for this noise level is very high. Okay, so that's one of the main reasons for the low quality of the data. And another possible reason is that this data has some bias. Okay, so anyway, here I did a simulation study. So here we have a true function that is in the solid gray curve. So you can see we have a solid gray curve here and here. And that is the true function f. Okay, so this is generated by a simulation study. So yi equals to fx plus epsilon I xi. Okay, and this f is a nonlinear function, which is this curve. Obviously, it's not linear, right? So the difference between these two settings is this one has the epsilon that is generated from a normal distribution with the variance is equals to 1. That's the standard deviation also equals to 1. Okay, but this one has the standard deviation is 0.1. So that means the variance is 0.01. Okay, so which one has high data quality? High data quality means less noise, right? So you can see this one has higher quality. Why? Because in this case, the data has the less noise. So the variation for the epsilon I is much smaller in this example, in this case than this one. Okay, so that's why you can see all these observed circles are very close to the smooth curve. That is because of the small variance for the epsilon i's. Okay, and then we can, of course, fit the underlying truth very closely, right? So we can, so here I showed two fitted curves. One, and we will talk about these two curves. These are the lowest smoother. These are the nonlinear smoother, okay? And with different parameters, okay? So you can see these red dot ones are not fitted well, but the blue dash curve with the span equals to 1/4 matches the underlying true function very well in here. But in here, although the blue dash one is still looks better, but that is quite away from the true relationship between x and y. But this one is much closer. So why they have a difference? Because this, in this example, it's more noisy compared to this one, because the standard deviation for the epsilon I, that's the irreducible error, is much higher in here compared to this one. So the data has higher quality for this one, but lower quality in here. So that's why the fitted function doesn't predict very well compared to this. Okay, so that's one reason. And also it can be affected by the complexity of the fitted functions. So you can see the span equals to 1/4 has more flexibilities and more complicated compared to the span with 2/3. So that's why the blue dash one fits better. Okay, so the complexity of fitted function also affects the accuracy of the models. Okay, so why do we estimate F? Two main reasons. One is the prediction, one is the inference. Okay, so like to make the accurate prediction of Y based on a new value of X. So that's, of course, focused on the prediction and which particular predictors actually affect the response. Is the relationship positive or negative? Is the relationship a simple linear one or more complicated? So these are related to the properties for the black box that we talked about, right? So what we can do is we have the data set with the X as input and output variable is the Y. That's the black box, right? Okay, so which is unknown. So what we do is we can use a statistical model or the machine learning algorithms to fit the relationship between the X and Y's and use that as an approximator, proxy for the box, which can approximate the relationship between X and Y's in the best way. And then we can use our fitted models to see which particular predictors actually affect the response and which is the relationship between X and Y is positive or negative based on the fitted model or the algorithm. So we can use our model to answer these questions if the relationship is linear or nonlinear. Okay, so that's why we need to estimate F first. Then we can answer these questions. Like these are the two examples, two real examples. So the first one is to predict how if we need to send out a mail to an individual who would like to donate based on the observation from 90,000 people on which they have recorded over 400 different features. So of course we should mail to the individuals that has the higher chance to donate, to make the donation, right? So how do we choose these target populations, right? So that's that. In this example, this is focused on the predictions, right? And the second example is to wish to predict the median house price based on 14 variables. So that is also based on the predictions. However, we also need to know, understand which factors have the biggest impact on the housing price and how big that effect is. For example, how much impact, how much premiums does a river view have on the house values? So that is related to the inference. And that also requires us to have a good estimate of F. Then we can use our models to answer these questions. Since our models has a good approximation for the relationship between X and Y. Okay, so that's, and how do we estimate F? So as I said, there are two groups of statistical learning methods. One is the parametric approach. That means it makes some assumptions out of functional form, like the linear assumptions, quadratic models, cubic models, like that. Okay, so the good side is that instead of estimating the function, we're estimating just a set of variables, a set of parameters, which are much easier task. So estimating a function is very difficult, but estimating just a few parameters, that is much easier task. Okay, so but the drawback is the form of the model can be too rigid. So that's usually related to the low prediction accuracy when the underlying F is very complicated. Okay, and another approach is the non-parametric approach. Okay? So we do not make explicit assumptions for the functional form like the neural network, trees, and also we have statistical models. Also allows to have no explicit assumptions about the functional form. So non-parametric method does not just exist in the machine learning algorithm. We also have non-parametric methods in the statistics field. Okay, so the good side is it can accurately fit a wide range of possible shapes of F because we have no explicit assumption on F. But the drawback is this non-parametric approach usually requires large number of observations to get a good estimate of F. So that's why when I do the consultings, I I have a few times the clients came to me and they says, "Oh, I want to fit some machine learning algorithm like the deep learning models on this data set," and I asked the client, "What is the sample size?" And they says just a few hundred, which I said, "No, there's no way we can do that." Because for these non-parametric methods, especially like deep learning, which is very complicated, usually has thousands or hundreds of thousands of parameters, and that requires much larger sample size. So a few hundred is not large enough to fit those non-parametric approach. Okay, so that's why the classical statistic models still works very well. Still are very useful tools because these classic statistical models like the multiple linear regression models, they are very useful and they are usually the best models to be used for those small sample size data sets. However, if you have a large sample size, then usually we can have much better models with much flexible assumptions. Okay? So this one shows a parametric uh, this shows a parametric model for the income example. So you can see our fitted surface is linear. That's a hyperplane, right? So, but for this approach, you can see compared to the previous one, this one is a nonlinear surface. So most of the data points are closer to the surface compared to this one. This one, we see some points which quite far from the fitted models. Okay, so you can see for the linear model, it works here, but the accuracy may not be that good. Okay, but for this one, that is called a simplate spline estimate, which is a non-parametric approach for the in the static modeling. And we will talk about splines in about 2 weeks. 1 or 2 weeks. Yeah. So for the nonlinear regression methods, like using the sink plate splines, which is more flexible and can potentially provide more accurate models. You can see in this case, most of the points are very close to the surface. And also the fitted curve is very smooth. But for this one, that's, I say, is a poor estimate. Why? At first sight, you think this may be very good. Why? Because this one, all the points are perfectly fits on the surface, right? So you can see the fitted residue are all zero, or very close to zero. So this is the best fit compared to this one and this one, obviously. So why this one I say is a poor estimate? Why? Because here you can see our model, let's say the most flexible assumption, let's say is yi equals to fxi, right? Plus epsilon I. Okay? And we have data x and I and y in the data set, right? So that's our data set. So we want to use the data to fit a model to estimate what? So we have the x, we have the y, and we want to fit a model, right? So let's say our model is called f hat. I put a hat here because that's our. So f hat is an estimate of what? Let me give you a multiple choice question. Just two choice, you pick one of them. So f hat is an estimate of y, or f hat is an estimate of f. Which is the correct? Or maybe I can add one more. F hat is an estimate of epsilon. Which one? First one, second one, or third one? Income. Yeah. So someone says income. So income is the first or second or third? Should be the first one. I'm talking about more general case. Okay? First. If you say first, that's not right. So f hat is not estimating y. F hat is estimating what? F hat is estimating f. You have to think about that a little bit. So that's the difference between the mathematics and the statistics. In mathematics, everything are determined. So they are deterministic. But in statistics, we have randomness included. We have uncertainties there. Okay? So here, the epsilon I is what? It's totally random. That's noise, which is irrelevant to the truth. Is that right? What is the deterministic part? So the model itself, it contains two parts. One is the random part, that's the epsilon. One is the deterministic part, that's the f. So we are focusing on estimating the f because there's no way we can estimate the epsilon. And also there's no use to estimate epsilon. Why? Because if I give you a new data set and you use this model to fit on a new data set, let's say X new. Okay? So what is the part that is related to the previous? The part that is related to here is the f x nu. But the additive part, the epsilon part, is different. This part changes, always changes, because it's random. Why it's random? Random means what? Random means it's not predictable. So to estimate the y is no good. But estimating the f, that's the goal. That's the right goal. Because the f is the unknown but deterministic part. We want to estimate f. If we can estimate f, then for a new sample, we want to make the new predictions, right, on the new data points. Then we can accurately get the fx nu. But for the noise part, we can do nothing. We cannot do anything on that because this is pure random. Okay, so keep that in mind. A good model is not estimating y, but estimating the f. That's right, it's estimating the f. Okay, that is very important. You need to make sure you understand that. Not just memorize that, but you need to really understand that. And that is one of the very important part in the statistics modeling. So for all the statistical models, we are not estimating y. We are estimating the underlying model. And that's deterministic part. Because the random error cannot be estimated, cannot be predicted. So that's why we call these epsilon called irreducible errors. So that's why if we have a model that perfectly passes through all the data points, that's not a good sign. First of all, that's not a good sign. Why? Because now the model is what? Is estimating what? Estimating the y or estimating the f. If the model perfectly passes through all the data points, the model itself is not estimating f, but estimating y. That is not right. That is not right. Because ideally, we should estimate f. But we have a name for this. If a model actually perfectly pass through all the data points in the training set, this is in the training set. And we have a name for that. That's called what? That's called overfitting. Why is called over? Overfitting, that means the model itself is too adapted to the data point. So what does that mean? That means, just in very simple words, that means this model is not focusing to estimate the f, but actually estimating the y. But the y is corrupted version of f with the additive noise. And there's no way and there's no use to estimate this epsilon. Actually, if you include this epsilon in the mod, if you are estimating the y, which is f plus epsilon, that actually makes the model performance worse if that model is applied to a new data set. Because the best model is the one that estimating the f correctly, right? It's not estimating the y correctly. So that's called overfitting. Okay, so that's why I said this is a poor estimate. So make sure you understand that. Okay, so this plot shows the trade-off between the model flexibility and the interpretability. So the takeaway message from here is when the flexibility of the model is low, that means the model is simple. Then the interpretability is high, like the linear model. lasso, subset, selection, linear regressions. Okay, so the interpretability is high. But when the model is more flexible, more complicated, okay, then the interpretability will be low. Okay, so that's the takeaway message. And this shows 3 simulation examples that I want to show you that there is a difference between the training and the testing errors. Okay, behaviors. So the training error and test errors behave very differently on the models. Okay, so let's see example 1. So in all 3 examples, okay, in all 3 examples, I use the solid black curve to show the true F. Okay, so here the Y, the response Y is generated by the Fx plus epsilon. Okay, so here the F, what is F? F is that black curve. Okay, so that's F. And those points, open circles, these are the Y's and X and Y's. These are the observed data points. Okay. Um, okay. So these are the circles are the observed data points. Okay. Um, Sorry for this. This. So these circles are the observed data points, and you can see the orange line. That's the fitted linear model. Okay, and we have 2 nonlinear models. One is the green curve, one is the blue curve. So the green curve is more flexible. You can see the green curve has more zigzags, but the blue curve is more smooth. Okay, so the blue curve is smoother, is simple compared to the green model. Okay, so now these, the right-hand side shows the errors and against the flexibilities that you can consider as the complexity of the models. Okay, the larger the flexibility, that means the model is more complicated, and the lower end, that means the model is simpler. Okay, so which model is the simplest? Obviously, that's the orange model. That's the green model. That's why it's on the left side. So the model flexibility is 2. Why is 2? Because if you're familiar with the simple linear regression, the degrees of freedom is 2 for the simple linear. 1 degree of freedom assigned to the intercept, 1 degree of freedom assigned to the predictor X, right? And what is the second more complicated model? So the second model, that's the green one. Uh, that's the blue one. I'm sorry. So the blue one, yeah, this one. It's smoother. It's nonlinear, so it's more complicated than the linear model, but it's smoother compared to the green one. So the most flexible one is the green one. Okay, and here the training error is that uh, gray curve. That's the training error. So that's the training error. Okay, So training error, that's the gray curve. And the red curve, that's what? That's the testing error. Okay, so let's see. The testing error is actually a U-shaped curve, but the training error is monotonically decreasing. You see the difference? So this is training, and this is testing. So for the training errors, if the model is more and more complicated, the training error is lower and lower. So that's why it's possible that it can pass through all the data points if the model is complicated enough. But that leads to what? I call it overfitting. Because overfitting means what? It's too adapted to the training data points Y. It's not fitting the F, it's fitting the Y. Okay, but if we have a new data point on the test set, you can see the performance are very different, right? You see that the test error is much higher than the training error. There's a big gap. You see that? So that is an indication for there's overfitting. So a common phenomenon for the overfitted model is what? Is that the performance on the training set is very good, almost perfect. However, if we have a new data set, the performance is very poor. Okay, and that is because the model is too adapted to the data point. It's not fitting the F, but fitting the Y. And that's exactly why I said this is a poor estimate, because it's overfitting. Okay? Okay, so if you understand this one, we can go over the example 2 very clearly. So in the example 2, you can see the true function is what? Is that black curve, which is very close to the linear line, right? So the black curve is very close to a line. Okay, so you can see for the, still we have 3 models. The orange one is the linear model. The the blue one is a nonlinear model, but it's very close to the linear. And this one is very flexible. So you can see the model for the, so the green model overfits the data points. So that's why the test error has a bad performance, much worse performance than the training. Okay? And the third example, when the true function is far from linear, you can see still we have a linear model here, nonlinear model, that's the blue one, that's the green one. Okay, so now the question is, which one is better? The orange one, blue one, or the green one for these 3 examples? Which one is better? Should we just choose the one that minimizes the training error? Like the green one is the one that always minimize the training error, right? Is that good? No, it's not. Why? Because ideally we want to have the model to be what? To be generalized to the new data points, not just the one that we fit the model, right? Because it performs pretty poor on the test set, much worse than the training case, right? So that's why the best one is what? The best one is the blue one, not the orange one, because the orange one is, we have a name. For this one, that's not, for this one, it's, this example is not that obvious, but if we look at this one, you can see the orange one is called what? We have a name called underfitting. So if you understand the overfitting, I think it's not difficult for you to understand underfitting. Okay? So underfitting is what? Underfitting is just opposite of overfitting. That means the model is too simple to catch the underlying F. Overfitting is too flexible, too complicated to fit the F, which actually not fitting the F, but fitting the Y. But underfitting means the model is too rigid, is too simple to catch the underlying true function F. Okay, so this underfitting, this overfitting, and blue one is the right model. Okay, so in practice, how do we choose the right model? The right model is the one that usually minimizes the test error, not the training error. So that's very important. Okay. Let's talk about these questions after the class. So here, underfitting, overfitting, these are, are shown in these examples, okay? But you cannot just tag the linear model is always underfitting, okay? So it really depends. If the underlying true model is linear, then this one is the right model. So that's why I'm saying that in these examples, like in this example, you can see this one obviously is underfitting because the truth is far from linear. However, in example 2, will you still say this one is underfitting? I would say maybe a little bit, but pretty good estimate. Why? Because the truth is very close to normal or is very close to linear. So this one, I would say it's a good fit. May not be the best, but it's one of the best. It's a good fit because the underlying truth, although it's not linear, but it's very close to linear. But this one is definitely not good. This one is the worst. Okay, so underfitting, overfitting depends on the underlying truth. But also you need to understand that in practice, in reality, the linear relationship is very rare in the real world. It's very rare. It exists, but rare compared to the nonlinear or more complicated. Okay, so that's why you can see the machine learning is very popular nowadays because these machine learning algorithms usually not assuming any linear assumptions, okay, which is very flexible models, very complicated, so that it can estimate very complicated association between the y and x. Okay, so there were two competing forces govern the choice of learning methods. I mentioned that before. That's called the bias and variance. Okay, so I talked about what is bias, what is variance. So the bias is basically is on the average, the model is missing the target. How much it missing the target? That's called a bias. Okay, and those simple models usually have large bias. Does that make sense? You can easily see that in the previous example. Here, the truth is that black curve, the linear model is here. Okay, what is the bias, let's say, when the x is close to 70? When the x is 70, what is the bias? The bias is, you see, from the linear model, we fit it here. But the truth is here. So the bias is that. You see that? We have a large bias because of the linear model. It's to have a rigid form. Okay? But here we have the bias is this way. So this one, the bias is what? The bias is positive. But this one, the bias is negative. Right? And this is the bias when X is close to 100. Okay, so you can see the simple model usually have large bias. However, the simple model is more stable. So the variance is low. That also makes sense, right? And I will show you some examples in a minute. Okay. So that's the simple model. But what about complicated models? If the model is more flexible, you can see flexible model tends to have low bias because it's complicated enough so that the bias between the truth and the models will be minimized, will be very small. But since the model is complicated, the variance of the model is large. Why? What is the variance of model? The variance is what? The variance is the model is related to the how stable that model is. If we slightly change the data set, will that cause a big change of the model or not? If the model is very complicated, a tiny bit change of the data points will cause a very big change. And that makes sense, right? So that's variance of the model. Okay, so in practice, you will see for simple model, low bias, high variance. But complicated model, low bias, but high variance. So that's why it's called a trade-off. It always goes in different ways. It's impossible to have an approach to get low bias and low variance. It's very difficult. Okay, so mathematically, we can show that the expected value for the MSE, mean squared error, for the new data point can be decomposed into three parts. This one is the variance of the model. This one is the bias square of the model. And this one is the irreducible error. What does that mean? That is the sigma square for the epsilon I. Remember in that model, y equals to fx plus epsilon, right? And the variance for the epsilon is what? Let's say we assume that is sigma square, and that is the sigma square. And that part is building the data. We cannot reduce that. So that's why it's called irreducible error. Okay? So I will show you some more details about math between that in a minute. So anyway, this is an example. So here I run the simulations. We have 100 data sets. Okay, each data set contains only 25 data points. And for each data set, I fitted a model using the Gaussian basis function. You don't need to know the detail. What is Gaussian? Anyway, these are the very flexible, nonlinear basis functions. Okay, and I used a regularized least square approach with varying lambda. So what is lambda? Remember in the lasso or ridge or elastic net, we have a lambda, right? So lambda is called a tuning parameter. Remember last time we talked about the lasso, ridge, lambda. For small value of lambda, that means what? The model is more flexible. So when the lambda decreases, the model is more what? The flexibility is increased. It's more complicated. Okay, so when the lambda is large, increased, then the model becomes simpler, less flexible. Okay, so that's the, so here I set the, in the left column, I showed not 100 data point. I think I showed about 10 or 20 data sets. You can see the lambda is, the log lambda is equal to 2.6. So lambda is the largest. So we have a large lambda. So in that way, the model is very simple. And these are the 20 fitted models. These are the red curves. Okay, and what is this one? In the bottom row. Okay, the red curve is the average from these 100 data sets, fitted model. So each data set, I fitted a model with that lambda, specified lambda. Okay, so what is lambda here? Lambda is equal to the exponential of 2.6, which is a quite large number. Okay, so I have, since I have 100 data set, each data set I fitted a model, which is a red curve here, and I take the average. So that's the average for these 100 models based on these 100 models. And the green one is the underlying true function. So the green one is the f. The green one is the f, is the true function f. Okay, so you can see when the lambda is small, the model is simple, you can see the bias is very large. Can you see? You see that? The bias is huge. There's a big difference between the truth and on the average, the model has a big difference. So the bias is large. Okay? Okay, now I reduce the lambda to a smaller value. So lambda now becomes to the exponential of negative 0.31. For this one is the exponential for the 2.6. But for this one is the negative, is the exponential for the negative 0.31, which is much smaller. And you can see these fitted models are more flexible, and the average of these 100 models are very close to the truth. So you can see when the model becomes more flexible, the bias decreased. And similarly, if we further reduced the lambda to negative, not 0.3, but negative 2.4. This is the smallest among these three. You can see when I take the average, it's almost perfectly aligned with the true function, right? So you can see when the model is more flexible, the bias reduces. Okay, now let's look at the variance. How to look at the variance? You can see among these 100 models, when the lambda is large, the model is simple, you can see the variance is what? Variance is very small. All these models are very clustered together. So that means it has a very small variation. The model are very stable. But when we reduce the lambda, the model becomes more flexible. So you can see the variance increases. And when we further reduce the lambda, you can see the model becomes more flexible. The variance becomes larger. You see that? So that is the conclusion from this simulation example. So that go with, let's, wait a minute. Let me go to this. So that go with this fundamental picture. Okay, when the model flexibility is low, when the model is simple, lambda is large, we have a high bias, but low variance. When the model is high flexibility, that means very complicated, that means it has low bias, but high variance. For the test error, from simple model to the complicated model, you can see there's a U-shape. From the training error, it's monotonically decreasing from simple model to the flexible. So which is the best point? The best point is the one that has the lowest values on the test error curve. So that is usually the best. So the best model is not on this side, is not on this side, but somewhere middle. Okay, so that's the relationship between the model complexity and the bias variance. Okay, now let's look at the bias and variance and MSE curve in the example 1, 2, 3. So the orange one shows the variance curve. The blue one shows the bias curve, bias square curve. So you can see when the model is, the flexibility is low, that means when the model is simple. So when the model is very simple, you can see the bias. The bias is very high, but the variance is very low. When the model is very complicated, you can see the variance is very high, but the bias is very low. Okay, and what is this curve? This is the MSE. And how do we calculate the MSE, and what is the relation between the MSE and the bias variance? Remember, the MSE is what? Can be decomposed, the expected value of MSE can be decomposed into three parts: irreducible error plus bias square plus variance. So you can see the MSE actually follows a U-shaped curve. Why we have a high value on this end? Because of the model is simple, we have large bias. So that's why we have a poor results here. Why we have a poor results here on the right end? Because the model has too high variance that cause the MSE to be large. So the best model is somewhere between that can have the minimum MSE. Okay. Similarly for the example 1, 2, and 3. Okay. Any questions so far? Okay. So for the classification case, so far we talked about the regression. Okay. What is classification? What is regression? How do we identify that? These are very simple. For the regression problem, the regression problem deal with the yi, which is numeric. Okay. And for the classification, it deal with the yi, which is categorical. Okay, so that's the difference. So for the classification settings, the error rate can be defined as this. This is the indicator function for yi not equals to yi hat. When we have that, that means when this condition holds, then we have a value equals to 1. Otherwise, it's 0. So this is the error rate. N is the sample size. Okay, and the Bayes error refers to the lowest possible error rate that could be achieved if somehow we know the true probability distribution of the data looks like. Okay, so let's see. This KNN, K nearest neighbors, this is one of the oldest machine learning algorithms and also commonly used machine learning algorithm to do the classification as well as regressions. So K nearest neighbor, how does this work? For any given X, we find the K nearest neighbors to the X in that training set, and then examine their Y values. And then we do the majority vote on the Ys. And if the majority vote shows, let's say, here, we have two classes, one is orange, one is blue. Okay, and we want to predict when the X is here. What should we predict? Then we just find the K nearest neighbors. Let's say K equals to 3. Then we find the 3 closest neighbors, which are these. And then we see their class label. So we have 2 blue and 1 orange. So what should we predict here? Of course, we should predict as blue because we go with the majority vote, right? So that's why we predict as a blue here. Okay, so that's why if we set the K is 3, in this data set, you can see this is the underlying boundaries for the 3 nearest neighbor results. So for each dot, we find the 3 nearest neighbors and then do the majority vote. Okay, so you can see it's that. Okay, this is the example that K is 1 and K is 100. So you can see which one overfits. which one is underfits. So you can see overfits, underfits still applies to the classification case, right? So obviously, when the k equals to 1, the model is more flexible. You can see the boundary is much complicated compared to the k is 100. And by the way, the black zigzag curve, that's the boundary, okay, from the model. And the true boundary, because this is a simulation, the underlying true boundary is that purple dash curve. Purple dash curve, that's the true boundary. So you can see, and when when the k is 1, this one overfits. But for this one, underfits. Right? Because the boundary here is close to a line, but the boundary is too flexible here. It's overfits. Okay? So you can see a good choice of k is when the k is 10. It's between 1 and 100. Okay? You can see the model fitted boundary is that black line, and the true which matches with the underlying true boundaries quite well, right? So that shows k equals 10 probably is the best value for the k. And this shows the training and test errors in the k&n case. So although the line is not perfectly monotone for the training error, but the trend is when the model is more complicated. Why I say model is more complicated? Because this is 1 over k. Okay, for so so for so for this end, k equals to what? K equals to 1. And for this end, k equals to what? K equals to 100. So in this way, the model is more flexible. More flexible. Right? And for this one, the model is less flexible. Okay? So you can see it's not monotonically, but the trend is decreasing. When the model becomes more and more flexible, more and more complicated, the training error decreases. But for the test error, you can see we still see a U-shaped curve. And this one implies we have an overfitting here. So what is the optimal K? So the optimal K should be somewhere around here, which we have a smallest test error. Right? So this is the classification case. So we talk about this. This is a very fundamental picture. So a cautionary note is George Box, who is a famous statistician and son-in-law for the R.E. Fisher. If you know ANOVAs, F-tests, or there are many tests in classic statistics developed by R.E. Fisher, who is also called the father of the modern statistics. Okay? So George Box once said, all models are wrong, but some are useful. Okay? So in practice, there is no true model, but a good model. So what is a good model? A good model should achieve at least one of the following. It can be an highly interpretable model that can be explained by some known facts and knowledge. It reveals something which is unknown or relationship among the variables and observations. And third is a model that can accurately predict on the new data points. Okay, so the first one focuses on the interpretability, the second one is the inference, the third one is the prediction. So an optimal model depends on the purpose, of the study, what do you mean the optimal? Okay, like for the third one, if you focus on the prediction accuracies, an optimal model means what? The model gives the best prediction results. Okay, but if you focus on the interpretations, then that optimal means what? Means the model that gives you the most interpretable results or can be explained by some known facts. Okay. So the optimal model depends on the purpose of the study, also depends on the complexity of the underlying mechanisms and the data qualities and the sample size. And we will explore more later. Okay, so go over the notes and we will finish that quickly next time. Okay, any questions? Okay, if you don't have any questions, let's stop here.